So 2.4, we start to introduce what we call complex numbers, and it's when you take the square root. So of a negative number. So if you look at x squared plus 1, if we would graph this thing, so when I graph the x squared plus 1, it is a U-shaped graph, a parabola shifted up 1, right? And my question would be, does this thing touch the x-axis? No. So what we've been talking about are finding the zeros of functions, solutions, and we're looking for where all these graphs touch the x-axis. Well, this one doesn't, and so we in the past have just moved on. And the idea would be if you solve this, you would subtract 1 on both sides. X squared equals negative 1. And then when we square root, we would say no solution because I end up taking the square root of a negative number, right? Now, if you think about what mathematics is, it's really created out of what people need. So we had, people do this like basic research, and we run into an issue, and then we try to prove it mathematically what's happening, and then the whole course of algebra started. The whole course of geometry has started. Leibniz and Newton are given credit for calculus in the 1400s. Okay? So you guys are studying mathematics that's several hundred years old, right? So at one point, somebody said, well, that kind of stinks because really, if I can only take the square root of 0 or more, which is what we talked about the domain, in a way that gets rid of half of all math problems. Can you imagine that? If every time we run into a negative number, we stop. So somebody says, what if we let I equal the square root of negative 1? How would that work? How can we continue on with mathematics? Well, if I equals the square root of negative 1, I squared would be equal to negative 1. And then we can keep on going. So the definition or complex numbers, that's created. I had a college professor that believed that all kids from the age of 4, when you learn how to count and do all your stuff, should work in complex numbers.
I agree.
And technically speaking, you have been working with complex numbers all your life. It's just that yours, instead of being pure imaginary, have always been pure real. You've always been working with, our standard form is A plus BI. You've always been working with some number plus 0 of the imaginary part. Okay? So, standard form is this A plus BI. A is the real number, and B is what we call the imaginary. It's with the I. So, we're going to add, subtract, multiply, and divide some of these complex numbers. Adding them, I believe, is very intuitive. I think if I say right now, I'm going to pause it. You guys add in the first one and let's see how many can get it right. So add your complex numbers together. All right, so I gave you some time to do it. And intuitive just means it's kind of in your brain already. Nobody has to teach it to you. You kind of already know the answer. So hopefully what you're thinking is, well, I'm adding 2 complex numbers together. It probably makes sense to put the reals together. So what happens when I take 6 plus 1? 6 plus 1? 7. What happens when we take negative 3 plus 2? What do you get? Negative 1. But the blue stuff has what with it? I. So hopefully it makes sense. When you go to add complex numbers together, you put the real stuff together, you put the imaginary stuff together, and you're done. That's all it is. The I denotes where the imaginary part is, but it, in a way, acts like a variable. So if you guys are able to use all your like term stuff or exponent stuff, you'll be fine. Subtracting. Same thing, you just have to be a little more careful with that sign. So I have the real parts are 5 minus 2. And my real part would be, or my imaginary, excuse me, would be -1 minus -4. So a lot of these things you probably can just do right in your head. What is 5 minus 2? 3, right? What's -1 minus -4? 3. Which one's the imaginary part? The green or the red? Red's imaginary, so we put an I there. So 3 plus 3i. So what you might see people do on these is put 5 minus 2 in parentheses. They might go plus, and then they might go -1 minus -4. And they might write the I behind that set of parentheses. It's really the same thing. You just pull them off the side, pull them off the side, do their parts. So adding and subtracting is not too bad. It's not bad either. We just follow our rules with the variables and what you might think of as exponents. So we'll start out by distributing. Two times 17 is 34. 2 times -5 is -10. That's pretty straightforward. What are you going to do in B?
Distribute again.
It's the distribution property, but some of you will think in your head like foiling or the box method, or you'll do something. So 3 times 5 is 15. 3 times 4i is 12i. -1 times 5 is -5i. -1 times 4 is -4i squared. Now what are you going to do?
You put the 4i squared for -4i squared.
Well, these are like terms. So we'll put those together. What else do we have to do? If you go back to the definition I circled, square root of -1 is going to be I. So I squared is -1. So under this I squared, I'm also going to write -1. So what happens when that becomes -1? What's -4 times -1? +4 plus the 15. I'm getting 19. And my like terms, when they go together, gives me 7i. Here, do not square both of them. It might help if you write it out. So you have 2 of those and you're multiplying. So I'm going to give you time to do it on your own. Very quickly. Multiply it out. Write your answer. Check with the person sitting next to you. Or near you. Okay, so here's what it's going to look like. I had you write down 1 plus 7i, 1 plus 7i. You get 1, 7i, 7i, and 49i squared. Don't forget to make the I squared -1, so you end up with 49 times -1, which is -49, plus the 1 out front, so we end up with -48, and then the 7i plus 7i is my 14i over there. Question? Okay, part D. Four times 4 is 16. 5i times 4 is 20i. 4 times -5i is -20i. 5i times -5i is -25i squared. So what's going to happen here?
20i's cancel.
These are opposites, so when you add them up, they go to 0. I squared is -1. So what's -25 times -1? Positive 25 plus the 16 is 41. Which is kind of unusual that you started with two complex numbers and multiplied them together, and you end up with what would be called a pure real number. There's no imaginary part to it. So, what we just worked on is an example of what they call complex conjugates. That is one piece of vocabulary that you need to know. There will be times it'll say, you're going to be working with the conjugate. So maybe it's multiplying by the conjugate. Find the product of this number and its conjugate. That means to multiply. So I'll give you one of the complex numbers, you write the other one down, and you multiply them together. So if you look, whenever you multiply conjugates, all I need you to do is what we call the first and the last. Because what's going to happen to the oi, the two middle parts? They're always going to drop off. So what happens then is when we divide by complex numbers, it isn't that we're actually using a division algorithm. What we talk about is not leaving I in the bottom. So it's more of a simplifying process. So we're going to take this. I'm just going to cover that up with multiplication. We're going to multiply by 1 plus I on the top and the bottom. So start with, what's 1 plus I divided by 1 plus I?
Why is it 1 plus I? Is it 1 negative?
Start with my question first. What's 1 plus I divided by 1 plus I? 1. So remember, you can multiply by 1 all day long. It'll change the way it looks, but it doesn't change the value. Right? If I take the fraction 1/2 and I multiply by 5 over 5, I get 5 over 10. Still means 1/2. Why is it 1 plus I? Because it's the conjugate of the denominator. So, Jeff, when I get done multiplying by the conjugate, what type of number am I going to have in the bottom or in the denominator?
Whole number?
It'll be, hold on, it'll be real, right? So right now, if we have an imaginary or complex number in the denominator, by multiplying by its conjugate down there, it's going to create a real number on the bottom, what we call like a pure real, nothing else to it. And that's what we want in math. So, let's do 2 times 1, 2 times I. So if you distribute on the top, anytime you multiply by the conjugate, I don't worry about the middle terms. So all I'm going to do is 1 times 1 and negative I times I. I don't worry about the I and the negative I because they're just going to add up to 0 anyway. So conjugates, just do the first 2 numbers and the last 2 numbers. What can I simplify? I squared is negative 1. What's 1 minus negative 1 on the bottom? Ends up being 2. To put it in truly A plus BI form, because oh, that's not up there. I have 2 things in the numerator, 1 thing on the bottom, so I can split them up. I can take the 2 over 2 and the 2i over 2. What's 2 divided by 2? 1. What's 2 divided by 2? 1 again times I, so you're just left with 1 plus I. So I'm going to give you a head start on B. What am I going to multiply by?
Or minus 3.
Look at the denominator, and all you do is switch the sign between them. So the conjugate would be 4 minus 3i. by multiplying by the denominator's conjugate, I'll create a real number on the bottom. But you can't take a fraction or a rational expression and just multiply the bottom. You also have to multiply the top by the same thing. So really you're multiplying by 1. So do this. Check with somebody sitting near you. What are you getting for an answer? Okay? So look here. Yeah. You gotta make sure you do the top. The top will be a full like foiling or box method. You have to make sure the 2 and the negative I both get multiplied times the 4 and the negative 3i. So you're gonna end up with four terms across the top. I squared, I'm just writing up here, right here it's negative 1. On the bottom, I can just do the first and last. So 4 times 4 on the bottom is 16. 3i, negative 3i is negative 9i. And again, that I squared is going to be negative 1. So look there first, make sure you have that. And then we'll talk about the simplifying. Normally, with complex problems, they will say in the instructions to write it in what they call A plus BI form. What they're talking about is separate the real and imaginary into 2 parts. So it's going to be some number plus or minus some other number. So when you get done multiplying everything out on the top, this becomes a negative 3 plus the 8. So that's 5. Then you have negative 4i minus 6i. Those are like terms. So that's where that negative 10i came from. So that should be your numerator. On the bottom, you end up with 16. That's negative 9 times a negative 1. So it's really 16 plus 9. So you end up with 25 on the bottom. When you look at this, there are different ways. Some kids will go, oh, divide everything by 5. Or some of you might say, what's 5 over 25 or 5 over 25 and hit math and enter on your calculator. But that's where the 1/5 comes from and the negative 2/5 I. And it's all coming from the fact that there was an I at the very beginning. There's an I in the denominator. How do you get rid of it? Yes, we want. This is also, in my mind, that's acceptable. But when they say write an A plus BI form, they are looking for you to separate it into 2 parts. In which case, then it's easier for you to see the reduced fraction sum.